So this is what we've got so far, right? Is that we've got this notion that we can take centripetal acceleration, multiply it by a mass, and we can get centripetal force, right? Okay, and then we've also got the idea that two masses in space are going to exert a force on each other using universal gravitation. So if an object is in orbit, that is like the Earth around the Sun or the Moon around the Earth or the International Space Station around the Earth, then this is the situation. And again, what a nice circle. Thank you. Okay. And then it's like, how do you top that? Well, you just draw, I don't know. That's not such a good circle. But this is my central body, right? Okay. So I'm going to call this guy the MC. I'm going to call this the MS, right? And then how do you spell satellite? Is that how you spell it? Or is it two T's? One T. I think it's either two T's and one L or one L. Is that right? Yeah. My brother had a car named a Satellite. It was, yeah. Maybe we need to. Certainly if Youngberg starts chanting, then we need to, right? Don't we? Yeah. Okay. So this is a satellite, and the satellite is moving at some velocity, or it has some period, right? It's got some mass, and the notion is that the centripetal force needed to make it go around the circle is provided by gravity. Now, we're going to make an assumption here, okay? We are going to assume that the mass of the satellite is much, much smaller than the mass of the central body. And you've probably never seen this before, because in math class they just do one of those, right? But sometimes in physics we get carried away, right? And so this thing here, that means much, much smaller than, or much, much bigger than, okay? And then it's like, well, how much is much, much? Well, much, yeah, much. It's much, right? Sometimes they put 3 in there, which is much. Oh, I'm just joking. It's just 2. Right? It just means that I would say that if you get to be more than 1% of something, you're not really much smaller than it. You're just smaller than it. Okay. I'll just throw that guideline out there. Okay. This approach works for the Moon and the Earth, and the Moon is just slightly more than about 100th the mass of the Earth. Okay. And there you actually get a little bit of error for this, but certainly for the International Space Station orbiting the Earth, or an astronaut orbiting the Earth, an astronaut or the space station is much smaller than the Earth. Yes? Okay. Here's the complication. The complication is that if they have equal mass, that would be the opposite of this, right? This guy is going to move, isn't he? Yeah. If they have equal mass, in fact, they're just going to do a little do-si-do. They're going to orbit around the center of mass, which is between them, right? Okay, and they have these, like there are binary stars out there that are doing that around their center of mass, which doesn't lie in either body. Okay, we're going to assume that this satellite orbits the center of the Earth. If that's the case, then isn't it true that the radius of the orbit is also the center-to-center distance? If the satellite orbits the center of the Earth, isn't the radius of the orbit the same as the center-to-center distance? Yeah. If they orbit, by the way, a spot in between them, then the radius of orbit is smaller than the center-to-center distance. Okay. So that's the case. If the satellite is much smaller than the central body essentially doesn't move. Okay. The Earth actually moves something like 10 meters per second because of its orbit with the Moon. Yeah. So it's not actually stationary, and that causes tides and stuff like that. Okay. Okay. So to solve these problems, basically you're just going to say that the centripetal force needed to make this guy go is either the satellite mass times v squared over r, right, or the satellite mass times 4 pi squared r over t squared, right, equals g mass of the central body, mass of the satellite over r squared. Yeah? Now, in either case, something's going to cancel. And this is very good news for us. Either case, something's going to cancel from both of them. What is it? If I set this equal to this or this equal to this, satellite mass cancels. Isn't that beautiful? I love that. Okay, so the satellite mass, and I'm only recently spelling that correctly. Okay. Now, none of this, by the way, is in the data packet as this. Okay. They give you this. They give you this, but not that, right? And then they give you this. So you've got to make this abstraction. Okay. So let's solve. Example 1. What is the velocity of an orbit 250 miles above the Earth? Okay. This guy, by the way, is way out there, right? 250 miles is the International Space Station. Sometimes is 250 miles out from the surface of the Earth. What do you mean by sometimes? Well, it's not actually totally above the atmosphere, so there's some drag. So it slows down and spirals in and gets close to the atmosphere. And every now and then they've got to attach a rocket to it and boost it back up into a higher orbit, which they do by just, by the way, speeding it up in its orbital trajectory, and it spirals away. But sometimes it's 250 miles above the surface of the Earth, right? So if this is the Earth, we're talking about an orbit that is like, because isn't the radius of the Earth like 4,000 miles, isn't it? So it's like a quarter of, or something like that. It's like a 16th of the radius of the Earth. That's a very bad picture there, but there it is, right? Okay. So the first thing we've got to do, if it's 250 miles above the Earth, is what do we have to do with 250 miles? Got to change it into meters, right? So miles, 250 miles, and a mile is 1,609 meters, isn't it? Something like that, right? So definitely we got to do that, right? So 250 times 1609. So if you run a 1600, you haven't really run a mile. You got to go 9 more meters, right? Okay. So this is 402,250 meters. Right? Now, is that the radius of its orbit? Is that the center to center distance? If it's 250 miles above the surface of the Earth? If this distance here is 250 miles? No. So what do we got to do to find the radius of the orbit? We've got to add the radius of the Earth, right? So this is like the hardest type of problem, right? So here's what we're saying is that if we've got, let's see if I can draw a small circle, okay? There's the Earth. Let's see if I can draw a slightly larger one, right? Okay, so here is the Earth, right? Okay, and if we are 250 miles above the Earth, that's this distance, right? Our actual radius of orbit is the radius of the Earth plus that, right? So we have to add 6.38, 10 to the 6 meters. Okay, so I'm going to go plus 6.38 E6. Okay. And our radius really is 6782250 meters, yeah? Put commas in there. So 6.78, blah, 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 et cetera, right? Okay. So that's our real radius. Now, what is the question asking for? What is the velocity, yes? Okay. So which one are we going to use? Are we going to use this equals this or this equals this? Top one, right? Yeah? Okay, so let's set that guy up, right? And this is what I think you should do, right? So mass of the satellite, V squared over R equals G, mass of the central body, mass of the satellite over R squared. This is what I think you should do. I think you should, the math is hard enough. These numbers are hard to type into the calculator. I don't think you're going to be successful just like trying to do algebra like this, like, right? Like plug the numbers in this case, and then try to sit there and solve. So I think you should solve it algebraically for the velocity, then plug the numbers in. So how do we solve this for V? Yeah, let's multiply both sides by R. So that R goes the way of the bison, and that's now just R, right? What cancels? Yeah, the satellite mass cancels. It still does. I just love to cancel things, so I put it there again. Okay, and then square root, what do we need to do? Yeah, let's square root that thing, right? Square root, there we go. Okay, so V is equal to the square root of General Motors over R, right?